Hello everyone, it's November the 16th. Alright, oh, we have a hot one today. Oh, I'm not expecting that, but alright, let's get to it. Let's see. Oh, this one looks new. It is new. Nearly everyone has used the multiplication table. The multiplication table of size m times n is an integer matrix where matrix ij equals I times j. I've never used that. One indexed, given three integers m and k, return the kth smallest element in the m times n multiplication table. M kth smallest. 10 to the fourth. That is huge. So kth smallest item. 3 by 3, fifth smallest. 1, 2, 3, 4, 5. No. Kth smallest, we have to sort it. So 1, 2, 3. No, 1, 2, 3, 4, 5. That's a 3. That's 2 by 3. So you always go diagonal, right? This 1, 2, 3, 4, 5, 6. Interesting question. I mean, every row, like we know each row is 1 times everything, 2 times everything, 3 times everything. Okay. These are all the same because that's like I times j, that's j times I. So these are the same. So if we are asking, is it sure that the ones in the middle will be bigger than the ones on the side? I think so. Because I plus j is 4, right? So, okay, let's do another observation. How about 4 by 4? So 1, 2, 3, 1, 2, 3, 4 by 4. We're 1, 2, 3, 4, 1, 2, 3, 4, 2, 4, 6, 8, 2, 4, 6, 8, 3, 6, 9, 12, 3, 6, 9, 12, 4, 8, 12, 16. It is most likely. Diagonal wise, everything at diagonal is I plus j is a certain value, right? So what we're asking is so we have, if I is 1, j is going to be k minus 1. I is 2, j is going to be k minus 2, all the way to I is half k, and j is half k. And then we're talking about, it doesn't matter, even or odd. So we're saying if k, let's say k is equal to, k equal to 6. How about k equal to 6? K equal to 6. We're going to have 5, right? and then so 1 times 5, 2 times 4, right? 3 times 3. It's 5 times 4, 3 times 3, so that's 5. That's, hold on, that's not right. Yeah, that's right. 5, 8, 9, 8, 5, right? That's the diagonal. So 3 times 3 is the biggest. How can we prove that? Like, given a k, then half a k, and let's say k is equal to an even number, odd number, even number. So k squared divided by 4, and the other one will be k minus, let's say, a b times b, right? So the hypothesis is k minus b times b is smaller than k squared divided by 4. So we can just do k squared divided by 4 minus k times b minus b squared, right? So if we want to do this, we can say it's 2k minus b squared, which is 4k squared minus b plus b squared, right? And it's minus 2b squared. That's not likely to always be positive, so there will be case. Right, there will be case that this one will be smaller than 0. When is it smaller than 0? When k divided by 2 minus b is smaller to square root b, or k minus 2 b larger than minus square root 2 times b. So that means k is smaller to 1b plus 1. K is larger than 1 minus square root 2 times 2b. So we also have b is smaller than k, right? So we pick a value. Let's say pick k equals 10. Right, if k is equal to 10, and we just need to see the smallest, because k needs to be larger than 1 minus square root 2. Oh, it's a negative value. So we're always larger than this. Okay, so this one is trivial. All we need to see is k must be smaller than that. So we should pick the smallest of the k. As small as a b, so what? K is smaller. So if the middle value is smaller than any else, then k must be smaller than the rest. Okay, so yeah, we can figure out just times anything, like not 5, but b is smaller than a half. B is smaller than a half. So times 1 is not going to do, but times 2 not going to do, times 3. There you go. So for I plus j equals 10, the middle value will be 5 times 5, but we will have a 3. A 7 times, no, the 7 times 3 is still smaller. What are you doing, man? Doesn't make any sense. Say if this is smaller than 0, right, which is the middle value. Oh, shoot. Yes, I computed wrong. It's plus. Oh, it will always be bigger. So the middle value will always be bigger than everybody else. Okay. Middle value is always bigger. But do the rest of the diagonal follow the same rule? So I can prove the middle value. Let's see. So what are we trying to do? So we have k is their sum. So I plus j equals k, and I have one of them, it can be, let's say, it's I and j, right? And the next one will be, if we move up, so I will be -1 if we move up, or diagonally move up. I -1 is j plus 1. So we'll compare these two, right? So ij minus I -1 j plus 1. Is this larger than 0 or smaller than 0? So ij minus j plus I minus 1. Come out ij minus ij plus j minus I plus 1. So it's I minus j minus I plus 1, which is as we go up until I is equal to j, right? So when we go low to high, what we have is before passing, right? Before passing the midpoint. So when we go low, then I is bigger, right? So I is always larger than j. Yeah. If I is always larger than j, then j minus I plus 1 will always be smaller or equal to 0. Because I is larger than j, or j is smaller than I, which means j is smaller or equal to I minus 1. They can only take integers. So with that, it's smaller. Therefore, in the lower half, if we use the diagonal here to divide the matrix, the lower half, as we go from bottom left to top right in this diagonal, the value is always increasing. And we can prove similarly on this side, the thing is always decreasing. Okay? That's another thing we proved. So we know the order along the diagonal. My final piece is this, the previous diagonal, always going to be larger than the next diagonal. So if the previous diagonal, we can just prove it, because this is the largest, right? So this is the largest, and this will be the smallest. If the previous diagonal's largest is smaller or equal to the next diagonal smallest, then we can prove it. So the previous diagonal will be, let's say, k squared divided by 4, right? So the next diagonal, smallest, because this is I plus j, and then if we go down, that's going to be k plus 1, right? Because this is 4, and this plus together, let's say this one was 1, 2, 3, so this is 5, right? This is 5. Wait, is this 5? Yes, it's 1 plus 4, right? It's 5. 2 plus 3 is 5, so it's 5. So now we're talking about the smallest will be 1 times k plus 1. K plus 1? No, it's 1 times k. 1 times k. So like if this is 4, right? So the k is 4. And next one k will be 5. And the smallest will be 1 plus 4. So the smallest value will just be k. So we're going to compare k squared divided by 4 minus k. And to see if this one is going to be larger than 0 or smaller than 0. Alright, this one we can do. This is k divided by 2 minus 1 squared minus 1. Alright. We want to see if this is larger than 0 or smaller than 0. Well, actually, nah, actually I realize that's not right. Like if we extend to 5, it's not gonna work. Diagonal of 5 is smaller than previous one. Nope. So that next diagonal is not always larger than the previous diagonal. Okay. Which means if we want to traverse, like say this way, right, it's not gonna work because it's not in order. That's fine, that's fine. Find other ways to do this. Let's see. Is this? Oh man, that's this value with the middle value. The middle value will be the biggest. Right, diagonal wise, the middle value will be the biggest of all of them, right? And we can count. That we can do. We can count how many values there are. It's 1 plus 2 plus 3, right, plus 4. So like 4 is going to be 1, 2, 3, 4, 5, 6. The sixth largest value. Well, the sixth smallest value is going to be 4, right? That we know, and we can say the 10, right? And then we have 2, so the ninth and 10th smallest will be 6. So the diagonal like this will be, but it also depends on the size of the thing, which we can compute, right? So for everything, like for this, we shall know, okay, this is 5, so we know there are 2 of them, all right? But still, this is squared, right? And we also have this situation, which make it a bit more difficult to handle. Difficult to handle. I don't think it's wise to try to figure out the position on this. How about we just iterate through? I mean, we don't iterate through everyone. We need to go to the cave, right? If I can, just go pick out the smallest. How do you know that they're the smallest? Like the next one will be 4, but we have 4, 4, and 4, right? Well, factor. How about factor? Or maybe dp? Like if we're given a value, let's say 6, right? We're given a value of 6. We know 6 can be expressed as 1 times 6, 2 times 3, and repeating. So we have 4, 6, right? So if we know the total number of values from 1 to 5, how many we have, if I know, like if I know the total numbers from 1 to 5, then I know the total number of 6, right? Then I can tell, right? So 1, total count of 1 is 1. Total count of 2, 2 is a prime number, so total count of 2 is 2. 3, prime number is only 2. 4, we can factor 4, right? 4, we can factor it. If we factor 4, we're going to get, it's 2 times 2, right? It's 2 times 2, which give us, well, we always have 1, 4, 4, 1, and then 2 times 2. So that will give us, I think there's supposed to be a formula to count how many different ways we can write it. But it's fine. We can just go factoring, right? We can go factoring. Like if 1 times 2, and that's 1, and then what times 2? 2 times 2, or 2 times 2 is only 1. Only position 1. So 4 is 3, right? We have 3/4. So we have these count, which allows us to build, let's say, build a prefix sum, right? So 1, 3, 5, and 8, corresponding to 1, 2, 3, 4. So if I want to find a fifth smallest, so I do a binary search, and the fifth goes into 3. If it's a sixth smallest, that's going to be 4, right? 1, 2, 3, 4, 5, 6. The seventh smallest. Oh, wait. That also depends on whether we can handle seventh smallest. Like if we have this 4 and this 4, right? Then we can say the seventh smallest is also 4, and eighth smallest is also 4, and ninth smallest will be 6. So what's the game plan? We go from the front and compute 1 by 1. 1, 2, 3, 4, 5. Jeez, come on, man. Really? 1, 2, 3, 4, 5? That is going to time out, I'm pretty sure. Like every single value, we're going to factor it. Okay, every single value we factor. How fast can we factor a value? Actually, factoring values is not that slow. Right? It's not that slow. I mean, it is slow, but it's all right. Okay, so let's say how do we factor then? We factor 1, right? So we do 1 times something, but then we need to check if that something is within a range. If it's not, then we just discard it. And next we go 2 times something. If it can be divided by 2, right? It's good. Then what? We cannot just do 3, 4, 5, 6. That's stupid, right? We need to factor the prime factors. So we just let's just say prime strip it to prime. So 2 times 2 to the power times 3 to the power times 5 to the power, right? And then given that, we need to figure out how many can be fit inside the matrix. So how do we figure out? Well, the total number of different combinations is humongous. It could be huge, right? It could be huge. And we're going to do this 1 by 1. Like in this case, 5, I want 1 and 5, but m is 2 and it's 3, so 5 we cannot reach. So 5 is discarded, right? And then 6. 6, 1, 6 discarded. 2, 2, 3. 2, 3 can be. 3, 2 discarded. And 6, 1 discarded. Alright? Okay. Okay. What if I give like a value? Divide by 2, discarded. And then what? Divided by 2 again. I'm going to create an exhaustive set. How do we do that? So we get given we have a factor, given a factor, then given a range, m and n, right? We have a range. Mainly it's the higher bound of the range. I want to know how many ways I can factor a value. So number of ways to factor a value given the range, the constraint on both factors. All right. So how do I compute all? Basically, this is a question of how do I compute all different factors? Well, to compute all different factors, we can say, okay, I want the first factor is 2, right? And then the remaining, I can find all the factors. I don't care. The remaining factors, I want to find out. And once I find out the remaining factors, right? Once I find out, then that would just be this times something times something, right? Something times something. And it could be 1, right? So I'll have the remaining something times something, and then when I come out something times something, I just 2 times the first and 2 times the second, and that's it. And this, I'm pretty sure I can cache it. How do I cache this? Like seriously, how do I cache this? How do you represent the state? The state is how many of the factors remaining, right? Well, what if let's say 1, and if 1, the factor is just 1 by 1, 1, 1, right? Let's call it 1, 1. 2 is 1, 2. And we only do 1. We don't have to do the combinations, like the permutation. We know we have the permutation. Okay, 3, and these are all prime, right? 4, so for 4, we find is divided by 2, so it's going to be 2 times 2, right? So 2 times 2, that's the factor we get. So always 1, 4, right? 1 is always there. So now we're going to find, so it's 2 times 2, so I say, okay, I'll set 2 apart, and then 2. So we look into the previous 2, I already done. 2 is 1 times 2. So this one will come out 1 times 2, right? So if it's 1 times 2, I can do 2 times 1 times 2, so 2, 2, right? Or I can do 1 times 4, so that's 1, 4, okay? So that's good. 5 is prime, so how do we do prime? We need a prime list. Let's get a prime list. That's fine. It's only 3 times 10 to the 4th. That's only 30,000. So square root that. It's only 173, right? That's the prime limit. We're gonna hit 173. Okay, so I got 5. How about 6? Well, 6, I do prime factorization, so we get 2 times 3. So I will say I will have the first one is 2, the next one is 3, all right? And actually, I only need to grab one of them. Yeah, I wanted to grab one of them because the second one we already have all the factorization we already done. So we grab 2, 3 gives me 1, 3. So 6 will give me 1, 6, or 2, 3. All right? That's it. 7 is a prime. 8 is interesting. So 8 is 2 times 4. So we just need the first prime value, right? So it's 2 times 4. So we isolate 2, so 4. 4 give us 2 different ways, 1, 4, or 2, 2, right? And then I just say, okay, for 1, 4, we can combine to produce 1, 8, right? And 2, 4. Now, 2, 2, we can produce 2, 4, but 2, 4 is already there. Therefore, these has to be tuples, right? So the tuples, and it's actually a set. It has to be a set, so we won't duplicate. All right. Okay. So, and as I'm computing every single one, yeah, that's actually, this might work. So for every value, we just have to do value one by one, right? And it'll be smaller than m times n, because the m times n's value will definitely smaller than m times n. So for every value comes out, I do factor, right? We do factorization. I only need to factor one prime value, right? Because the rest, we have already done it before. And then we check on that, grab all the factorization from that, and then combine it with the current one, then we can get my new one. But I need to make sure that every single one will be, not duplicating, which is fine. So once this is done, well, this can grow quite large, right? This can grow quite large. The number of factorization can grow quite large. But on the other hand, do I discard the ones that do I discard, like, if there's something, right, that I cannot use, like here, right, like here, the factorization of 3. I say it's 1, 3, but I can only use it for one of them. I cannot use it for the other one, like 3, 1, we cannot use. Well, then we need to keep 1, 3, 4, right? So 2, 2 cannot be used. If 2, 2 cannot be used, do I discard 2, 2? Wait, 2, 2 get used, my bad. 1, 4. 1, 4 or 4, 1, they cannot be used. Well, if they cannot be used, do I discard it? Well, what's the consequence of discarding it? Well, the consequence is the next time if some value comes in, right, and I want to check, let's say 8 comes in, I want to check, I need 1, 4. But if 1, 4 is already, but it's no good, it could be one is good, the other is no good, or both is no good. If both is no good, then I have a new one comes in, I need to multiply, then that won't be good either. If only one is no good, then I have a new one comes in, which means one of them is too big, then it's no good. So yes, I can discard immediately. If there is something, if there is some combination, right, that does not fit, then I can discard it already. Okay, so by doing this, we are also counting, right? We're counting how many values in total we have so far. Like we can do this, right? 1 is 1, because we have one way. 2, we have 2 ways, right? We have 2 ways. 3, and we find out 3 is going to be 1, 3, right? It's 1, 3, or 3, 1, and we say 1, 3 is good, 3, 1 is bad, so we add 1 value, so that's 4, right? So for 3, it is going to be 4 values, and we're looking for 6. So 4 comes in. 4 comes in, we obtain 1, 4 or 2, 2. And 1, 4 is deemed impossible, so we don't count it. 2, 2 is good, and that's only good for 1, so we have 5. Now 5 comes in, so 1, 5. 1, 5 is outside the range, we don't count. Oh, we don't count. Does that mean we don't even record 5? Yeah, we don't record 5. We simply don't record 5. Like if it's not even in existence, then we don't record 5. Now 6 comes in. 6 comes in, we have 1, 6 or 2, 3, right? 1, 6 is no good. 2, 3 is good. That's 6. And 3, 2 is bad. So after 6 is done, we got value 6. And that is our result. So at the end of each value, we have the total number of counts. And if the count is smaller than the target, smaller than k, then we keep going. And once the first time that the value is larger than k, then the specific value that makes it larger than k will be the result. All right, let's follow this idea and see if we can code something up. Okay, so I have high confidence that this one will work. It's all about factorization, all about factor. Actually, some idea that we had I won't say last week, but yesterday, right? We have this idea yesterday of factoring. But yesterday we don't really need factoring, but today I feel like we need factoring. All right, so before we start, we do need to do one thing, which is to grab the prime number. Okay, we need to grab the prime number from 1. So prime numbers smaller than, well, we have 173, right? Let's just get 174. Is this, just go prime number list. Prime number list, that is not a friendly format, but I will take it. Oh, 173 is, so we'll just go for 173 then. All right, we need to formatting this. Oh my goodness, this is terrible. Nope. How, this is stupid. I need a better website. It's a copy and paste, I cannot get anything. Dude, this one has, I don't think this is a good format either. Well, it's better, definitely better. So we can do a little bit of processing. Yeah, we don't need 179. Okay. So the only processing we need is remove this, and we're just gonna go search, right? What we need is we're gonna search for all these, and we're gonna swap with this. So replace all. There we go. That is our prime list. So we need to copy and then paste the function. All right, so primes, right? So we say primes, so equal to, and it's going to be every value. That's fine. Yeah, we can just go. We can make it a list. Make it a set. There's no reason to make it a set. It's okay. List will suffice. List will suffice. Giant list. Okay, that's the primes. And then we need a count. All right, we need a count. It'll start with 0. Actually, let's go. Count is 1. And we need another one is factors. Right? That's gonna be a this. And every single one is going to be a, oh, do we want a set? Hold on. All right, I think I said we need a set. Well, we need a set just so that we can avoid duplicates. Yeah, let's do a set. I think it's fine. So a set, and inside it's going to be a tuple. Right? We can only do a tuple in a set. Okay, so that's the factors, right? Now, what we're going to do is for I in range, actually not I in range, I equals 2, while count is smaller than, well, if count is equal to, so if count is smaller, then we'll definitely go to the next one. So yes, count smaller than k, right? Okay, now we have I, we need to factor I, right? So we're going to find the first factor. So we're going to say, the pi, so the pi is 0, right? Prime. We're going to go through the prime and find the first one that, okay, the pi is 0. And then we say while primes pi, right? While I mod this pi plus equal 1. Until the first one that it gets out, right? That means that is the first one. So then we have a factor, right? So we can call factor 1, factor 2 equals primes pi. And factor 2 is going to be I divided by primes pi, right? Now we have two factors. Now we're going to go inside the factors to find all possible factors, right? So we're going to say for fact, right? For fact, no, fact sounds weird. For doesn't matter. So for the for A and B in factors F2, factor 2, right? So that's going to be just, these are popping out. And for every single pair, what we can do is we can compare, right? So we have two options, right? So option 1 and option 2. So we're going to say A1, B1 will equal to A1, B1 will equal to A times F1 and F2. No, A times F1B, right? A2, B2 would be A and B times F1, right? So that's two possibilities. Now when I check, we say, now A1 and B1, they can go two ways, right? We can swap them. So we have two ways. We have to do two rounds of comparison. The first round, we can say if, for that, I think a better idea would just say def check valid self of M and A and B, right? Return Boolean value. So we say if let's say what? A is smaller equal to M and B is smaller equal to M, or, alright, it's only two possibilities. If this or A is smaller equal to M and B is smaller equal to M, then we return true, which just means we're going to return this, right? So for this, we're simply going to say if self.checkValid mn a1 b1, if this is valid, then factors I, right? Factors I dot add the min of a1 b1 and max of a1 b1. And this is good, so count going to be plus equal 1, and I just realized this has to be from collections, import, default, dict. This is not going to be this, it's going to be a default dict. Default dict going to be a set, and I'm going to say factors 1 dot add 1 1. All right. And then I say if this is good, we're going to add. So I'm going to repeat this. means if B1, A1, oh, we only added once. All right, we only added once. Huh. Do we have to add all these times? Right, if this is valid, then we just add again, but then we, because it's a set. Yeah, I feel stupid, but let's just do the stupid way for now. So we'll do the same thing as A2, B2, right? A2, B2, oh Lord, all the repetition. A2, right? And this is going to be B2. Right, A2, B2, B2 or A2. Can we do something smarter? Let's do it here, right? This one is do A smaller than M, B smaller than N, right? Because that's A and B. We're trying to see if A and B fit. Yeah, hold on. I already did it. I'm already saying if A smaller than M and B smaller than N, that means we're going to fit A on the row and B on the column. And this I'm going to fit A on the column and B on the row. So that's already 2. So actually I'm going to do int this plus int this. And I'll return the int. So when I just check valid of this one, right? I'm going to say check 1 equals, I do need a value. So check 1 equals this. I'm going to say if check 1 is not 0, I'm going to do this, that's equal to check 1. Alright, and then we don't need this. Yeah, I'm going to simplify it. So now we're going to say check 2. If check 2, I'll have to do this one as well. So it's just check 2. So check valid A2, B2. And if check 2, when dot add A2, B2, max A2, B2, and it's actually we don't have to because A is smaller than B, so this one definitely is A2 and B2. So I can just add A2 and B2 in this one, A2 and B2. This is less clear because I have to time something, so the size can swap. The size can swap. Okay, add this count at check 2, right? And then once everything done, all right, factors I added, going back. So count updated going back. If it's equal, comes out. Then, or if count is larger than k, come out. We'll just return I. Did you update with I? I did not. I plus equal 1. All right. It also could be like something comes here, and then it find out there's nothing. Right? It's a 0. It's a 0, so nothing changed. I just keep going. Okay. All right, let's run some test case. So what do we have? What we have is 3 and I think first one 335. 335 shall return 3. Next one is 236. 236 shall return 6. Okay, here we have M and K. Right, M and K, and this is going to be find M and K. Run it. First one pass, second one fail. That is a tragedy. Why? First one pass, second one fail. All right, let's print count factors All right, these are the two main things. 1, 2, 3, and count as 7. Oh, count 7. 1, 2, 3, 4, 5, 6. There's no 7. All right, what the heck is happening? Let's print A1, right? A1, B1, and check 1. And A2, B2, check 2, right? A2, B2, check 2. All right, A1, so it's 2 times 1. Let's also print F1, F2. That's the actual factor. All right, so the 2 and 1. Oh, I see. Yeah. That's the same thing. 2 and 1. So we get 2. So we have 1 and 1. So this one, you know what? You know what? It's not worth it. I have a better idea. Or, right? I return Boolean value. So if this, right, then we add it, but we don't add a count. Here, same thing. If this, add it, but don't add a count, right? So every single one, when we add it, so count will equal to len factors I. All right, so len factor I. Okay. Index out of range. That is bonkers. How do we hit index out of range? What? If 1, 2, 1, 3, 1, 2, 2, that's 4, 5, 6, 7. The count is still not there yet. What the heck? I'm gonna do I and count. 6 count as 4. What in the world? 1, 2, 3, 4, 5. Should be 6. Oh shoot. Dang it. Yeah, because it could be rotated both ways. Oh man, this is how should I put it? Well, we cannot do that. And we check valid. And we say one of them is valid. Oh, I think this is the last piece. This is the last piece. No, we cannot do a len because it can do both ways. So basically for this, if I figure out, okay, for this one, we definitely, how about this? We still do int. For this one, we still do int. We're always going to do int, right? Plus int. Int and int. And that's going to return integer, right? So we do check 1 equals this. And if check 1, we do this and count plus equal to check 1, right? But this, before we do it, when they check, right? We need to check. We say if A2, B2 is not in factors I, right? If it's not have not been counted, then we do check 2 equals self.check valid m and A2, B2, and we say if check 2, we're gonna add it, right? And then count plus equal to check 2. But there's one more thing. There's one more thing. If A2 and B2 are the same, all right? So that is, so this one minus int A is equal to B, right? If they're the same, we can only count once. If A is not, this will be false. Yeah, so we have one more thing. So count, we don't do it here. Then we run, and we're almost there. We're almost there. So we'll print I2 will be, well, that's before the count. Well, it'd be better to do it after the count. Let's do it after the count, so it'll be easier to figure out. All right. 2 counts 3, 3 counts 4, 4 counts 5, 1, 2, 3, 4, 5, 6 will count 6. But when we come out, so I have a count, right? And I plus equal to 1, and then it will go up. I already incremented. How about we don't increment? We need to increment I on the top. All right, let's increment I on the top. So I, we will increment on the top, plus equal to 1. So on the start, with 1, right? Yeah, we start with 1, count, and this one is give us the right result. And we don't need this, we don't need this. Okay. Now let's run a few test cases here. I mean, this one is actually possible to run like our own test case because I can just brute force it, which is completely fine. All right, so we're gonna go, let's say 100 by 1000, and we want to find what's today's date, 11/16. How about that? Let's see how fast we can get it. Index out of range. What? Oh. Yeah, we hit a prime. Oh, that is a thing I didn't think about. All right, so while I is smaller than a len, geez, so count len prime, len primes, okay, len primes, right? So while I is smaller than, while I smaller than len primes, and then we do this, and eventually, all right, eventually, pi plus what? IPI, it's pi. And then eventually, I'll hit something that does either the divide or something that does not divide. Oh, I see the problem. I see the problem. I have to go through every, oh no, nah. Now we're talking about have to get a lot more prime numbers. Oh, yee. Oh, we need to get so many more. We're gonna get n times n. Right, we say it's smaller than m times n, but we need to get m times n. That's a ton of prime numbers. But we're not afraid. Let's just grab them. Let's just grab them. So list of prime numbers. List of prime. How many? 5,000. The first 50,000. 50 million. Let's go first 50 million. Oh, Jesus. I want to tell you the first prime, the last prime. What are we going to have if it's 3 times? If it's 3 times 10, so it's 9 times 10 to the 8th. That's 900 million values. We're going to get that many prime numbers? Jesus. Come on. This is bonkers. This is bonkers. What do you say? Well, we have to build a prime list along the way. Ah, God. All right. Yeah, it is not working. It is not working. We need to build the prime list along the way. So if we want to build a prime list along the way, all we need to do is to find how many prime do we need? 2, right? If we want to build along the way, we don't need 2. So what? So we say, and then we cannot do len prime. It has to be 1. And this has to be len primes. Right? So we say pi start from 0, and if it's divisible, when it would break out. If it's not divisible, pi plus equal 1, blah blah blah, until the end. When I break out, right? When I break out, I'm going to see if pi is equal to len primes. That means the current value is a prime. Then we say primes dot append I. That's the current value. And after I appended it, then factor 1 will be the prime, which is myself, and this will be 1, right? So it'll be myself and 1. Then they'll go into 1. Okay, so I think this one shall still work. Yeah, it still works. Let's see. Now we're gonna run back. Same thing. Go it again. Nope. Nope, it's not correct. Okay, we're gonna do a smaller case. Let's see 4 by 4. Right, 4 by 4 is small enough. 4 4 is 16. Let's do 14. Ah, 14 is not correct. Okay. Maybe it's not correct 3 by 3. Maybe that is just a fluke. 3 by 3. How about we do 8? 3 by 3 is right. Alright, 4 by 4 then. We're gonna run everything in 4 by 4. Just fine. So we're gonna do 4 by 4 starting from 4 by 4. We're gonna have 1. We're gonna do 1. Yeah, on the list 2, 3, 4. Oh. Alright, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 15 and 16. Alright, second one is 2. Third one is 2. 1, 2, 3, 4. Fourth one is 3. Fifth one is 3. Sixth one is 4. 7 is 4. 8 is 4. 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, 9 is 5. 10 is 5. 11 will be 6. 12 will be 6. We don't know 7, so 13 is 8. 14 is 8. 17. No, 15. 15 is 9. And then we have, oh, there is no 5. Dummy. Ah, jeez, there's no 5. 6, immediately 6, 6. Jeez, there's no 5. I was reading wrong. Then 8, 8, 9. Right, 8, 8, 9, 12, 12, and 16. Alright, this is a comprehensive. Alright, we fail starting from 9. Okay, it's fine. Let's isolate 9 and take a look at our count, right? So we're going to print I, factors, and count. Alright, so 2 will be 3, that's correct. 3 will be 5, that's correct. 4 will be 8, that's correct. 5 will be 8 because there's no 5. 6 will be 10, that's correct. 7 will be 10, that's correct. 8, oh, that is wrong. 8 is not 14. 8 is not 14. 8. And we don't have 1 times 8. That is tragic. Ah, I see. Definitely we don't have 1. Okay, so, Alright, so for each one, we need to check, yeah, before the prime factoring. Oh, how about, that's our prime. Well, it's not a prime, but, you know what I mean. But then I'll stop at 1. Nah, that's not what we have to do. 2. Because 1 will be divisible by anyone. So I get a prime, right? And then actually 2 pairs, like 8, I'm missing a pair. Oh, hold on. 8, that pair does not exist anyway. But do I get 1? Oh, I do, because it's 2 times, so 4, right? 4, what we get is 1, 4. So I do get 1. So 1, 4, I get 1, 8, or 2, 4, right? And then this we get because it's a second value. Oh, I see. So I have to do this for every single one. Every single one. A1, B1. Not in it, then do it. We have to check for everyone. We check for everyone, still not right. Now we get 14. Yeah, 8 will be 2 times 4, right? And factor 4 is 1, 4, 2, 2. So first come out is 1, 4, right? 1, 4. This one will give us 2, 4. 2, 4 is not in, and we can check 2, 4, 2, 4. This is good. This is good. So 2, 4 will return 2. So count plus equal to 2. That is correct, which will give us to 12, right? And then this one, that's 1, that's 4, that's 1, 8. Now 1 is not in, I'm going to check for 1, 8. So 1, 8 is false on the first one because 8 is not smaller or equal to 5, 4. And also this is false. So false plus false, that's 0 plus 0 minus, what if it's a true here? I'll take a negative value. Well, I think that's not possible because if these two are the same, then the value is huge. Then, well, to prevent it from happening, we say this one, we're going to take the maximum, right? How about we take the maximum of this and 0, right? So if in the unfortunate case that we have a negative value, we'll always return 0. Okay? So it's 1/8. So 1/8, that's false, equal to, that's false, so that's 0. So 1/8 is supposed to be 0, so we don't do it. That's why 1/8 is not in there, okay? So next round comes in, we have 2/2 comes out. So 2/2 comes out. The first one is, I see. Dang it. I need to make, I know what's wrong. Dios mío. So it's gonna be this and max. This is just, well, if we do this, then I don't have to do this, right? This is just gonna be A1, B1. And in here, AB is factor, so it's guaranteed, right? First is one of the second, so this one we don't have to do the min max. This is the first one we do the min max. There we go. Now we pass. Now we pass. Okay. Actually, we'll run the remaining. They all pass. Okay. Now we're gonna try it again. Okay. Same thing. 100, 1000, 1116. Run it. All right. Let's do this. Submit. Pending. Judging. Oh no. Oh no. Oh no. Ugh. I think we timed out. What the heck? We timed out. Shoot. Shoot. Now what? I didn't expect this one to time out. I thought it's fine. I thought it's fine. Yeah, it takes a long time. Really a long time. Jeez. I mean, this is fast, right? I think this one's fast. So, the prime part could be slow. Can we do something about it? The prime, like if you think about it, we're doing this one every single time. For each new I, we have to run all that. I'm gonna give it another 15 minutes. How about 15 minutes? If we can't do it, we're gonna call it. We're factoring. Yeah, that's the thing. I know the prime goes big, and eventually it grows so big. Hold, let me think. Why? Oh yeah, it's because the values we're gonna hit is gonna be larger than 3 times 10 to the 4th, right? We're gonna hit a huge value. It's this times 3 times 10 to the 4th, right? So that means the prime list is gonna be huge, right? It's gonna be a huge prime list. Well, actually, I just realized something. 3 times 10 to the 4th, right? And m times n, we only need to go to 30,000. 30,000 prime numbers, right? So I only need 30,000 prime numbers smaller than 30,000. Do I have? List of 50,000 primes. No, this is going to be bad formatting. Oh, it's not. It's not that much, right? It's 30,000. Let's be sure. Go on this one. So now it's much smaller, right? So I think the reason is I just keep going, right? If it's not, then I keep going. So the value is close to prime, but we don't need to. We only need the square root. I only need square root. So that I think can shave time off. Actually, why do you do this way? Why? Right? We can do it. Just instead of doing this, it's not pi smaller or equal to this. We're gonna do we are going to do its if while pi is smaller than this, right? And I is this, and the prime is a smaller, right? And we probably need to just do it once. So sqrt equals math.sqrt. I mean, there are two ways to do it. And one way is just go bonkers at this. This is how many? That's actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3,000. 3,000 in length. And we can avoid do sqrt for each value. I'm taking it. Right, I'm taking it. Okay. Oh, this is going to be ugly. This is going to be ugly. They probably all what they call like, woo-wee. What the heck is this? All right. And then this is just I can avoid doing math.sqrt. And then I do the same thing, but we have a limit. I'm not sure. Still slow. Still slow as hell. Oh, because I'm adding. So now we don't add, right? So if this equals this, then then you have a prime number, right? And you have a prime number. Yes, the current value is a prime number. Else, current value is not a prime number. Now we do all these shenanigans. If the current value is a prime number, then I have a 1 and I, right? Basically, it's 1 and I. If it's a prime number, we have 1 and I, and then need to go through the same check, right? So I'm going to say check equals to self dot check valid mn, small one first, larger one second. The small one will be 1, larger one will be I, because I is prime, right? So I'm going to say I is prime. So we'll do check. I'm going to say if check factors I dot add 1I count plus equal to check. Try it again. I'm actually going to try on my end as well. Oh, this one's going to look ugly. Ugly as hell. Yeah, but still not working. Still not working. Yeah, these pass, but Alright, so no, this is not working. Factoring not working. Okay. What else can you conjure up? Don't know. What else can I conjure up? Yeah, because factoring is, we have to go through every single one. And at least if it's a prime number, we have to go through all this. It's a couple thousand. Yeah, that's definitely adding to the toll. Adding to the toll. And every time counter will just plus. Yeah, this is not working. Alright, so we know first row and the first columns are the same. Alright? But we'll have stuff in a second. Yeah, that's the thing. We cannot sort them. Four, 6, 8. Right, these are the times 2. These are times 3. Right? So is that times 1? If I know m times n, right? So I know for each row how far it extends. First row. So the second row, right? For every value in the second row, are you saying we can insert into the first? Ooh, that might be an interesting idea. Might be. So based on n, we have the first row. First row is going to be 1, 2, 3, 4, all the way to n, right? So the second row, for each value, right, that is smaller than n, we already occurred in the first one. So we just increment. For the value that's going to be larger than the first one, we just add it to it. And for the third one, but what's the difference between this? This basically you're doing counting sort, right? We still have to go through every single one of them. That's still OMN. That is OMN. Come on. That's actually worse than OMN. Oh. Hint. No hint. Binary search. Binary search. Binary search. I feel it might be binary search. Binary search. So given a value and we binary search it? Or like, I know the largest value, I know the smallest value. Do I even know the largest value? The smallest value is 1. The largest value is going to be the lower right. Yeah, it's going to be the lower right. So this is the largest value. This is the smallest value. So the ones will be in the middle, right? So what? Binary search. And we need a count. Alright, no idea. Alright, solution. Brute force is not going to work. Even with this, a better brute force will not work. Next heap. Maintain the heap of the smallest unused element of each row. Then find the next element is a pop. Hold on, what's this next heap? Smallest unused element of each row. Then find the next element. I for I in range 1 to this, and heap 5. So the first, huh? That is just so simple code. Wait, what? So that's row. So first row, what is this I? First row, first value. Second row, second value. Third row, third value. Well, those are the biggest. Right? Those are the biggest value, but not necessarily the biggest among them all. And the heap file will be heap file based on this value. When I pop the value and the root. in range k. Okay, so I want to count the kth one, so I'll have the value, which is the smallest value among all the roots. Ugh, I don't like the root, among all the rows. Okay, smallest value among all the rows. Well, second row, smallest value. Third row, oh, that's the smallest. So the first row, smallest value is 1. Second row, smallest value is 2, right? So for each one, I'll pop. That's the smallest value, and this is the which row it is, right? So the next for that root is going to be the value plus the root, yes, right? And then we're going to check if the next value is smaller than the root is row number times column. If it's smaller, then I can put it in. So I push it in. And we'll keep going, keep going. Oh, great solution. Great solution. Geez, they time out this one as well. Nice. So we use a heap. I want to pop out the smallest unused value of each row. And because we're popping out the smallest every single time, so we can just iterate through k, right? And every time smallest pop out, and then we find the next one, and now I push back in if it's pushable, and then we go back in. So it's OK. This is OM. It's O log M. It's OK. OK log M. OK M log M. Why OK M log M? Is heapify M log M? Each pop and push is really. Wait, pop and push is OM log N? Heap pop time complexity. I thought hop. ON to build a heap for the pop, so it will be worst case ON log N. Pop is 01. No, it's not 01. I know it's not 01. Yeah, it's O log N. That's what I know. It's O log N. How about push? Yeah, it's O log N to push and O log N to pop. I don't understand. This one says it takes OM log M to pop and push. I don't agree. I think this is OK log M, which is OMN log M. Let's see if Yeah, it's log n. Yeah. But they time out this one as well. Let's just copy and paste. Let's just see how my code is just too ugly to look. Jeez. This is so elegant, but it still fail because the K is just huge. Yeah, the K is just huge. Wow, so this also doesn't work. Much better than the first one. OMN and log MN. This is OMN log M, so slightly better. Binary search. OM log MN. As K and N times are up to linear solutions won't work. Okay. I see. Linear will not work. Therefore, we try to do it log n. We need a log solution. It's true if and only if there are k or more values in the multiplication table that are less than or equal to x. But x is large enough to be the kth value. Therefore, our answer A. Whenever x is larger or equal to A, this one's true. When x is this one's false. Oh, loop invariant. Enough high is true. At the beginning, this is true. It is set to a value that is enough. Medium. Lowest such value at the end of binary search. How many values are less than or equal to x? For each of m rows, the ith row looks like this. The largest. Oh. Are we doing binary search on every single one of them? Oh, I think I know. So we're gonna do overall binary search, right? And then when we hit the middle value, we will loop through every single row and count how many are smaller than that. Oh. But no, they don't do binary search on that. We can, right? The largest possible value, so that could appear is, we can directly do k equals x divide. Yeah, so dumb, man, you're so dumb. We just do divide, right? If k is really big, then k is larger, so in total there will be minimum values. And after we have count how many values in the table are less than or equal to k, by definition we want to know if that count is greater or equal. Oh, wow. Let's code it up. Let's code it up. Binary search. So it was correct that I was trying to find a total number of values, right? That's so far. That idea is right, but the way I am finding the total number of values is just dumb. The right way is given a value, right? So low is going to be 1, high is going to be m times n, right? That is high. And then, low is smaller than high, right? Mid equals low plus high. divided by 2. Now we bias against low, so it has to be low plus equal to 1. Now what? Now we're going to find the total number of values that's smaller or equal to mi, right? So I'm going to say for r in m range m 1 to n plus 1. All right, so that's the row. So first row, second row, all the way to the mth row. Well, that's the factor, right? So what we're going to do is have a counter. And for each one, I say count plus equal to the minimum value of n and what? Mi divided by r. All right? And once we're done, we're going to check if count is smaller than k. All right? If count is smaller than k, that means it's not big enough. Then low equals mid plus 1. Otherwise, if count is larger or equal to k, right? If it's larger or equal to k, well, if counter is larger and it's too big, then high will equal to mid. That actually happens. Say Aleph count is larger or equal to k. Finally, we'll have a condition that count is equal to k. If count is equal to k, we just return m, right? And we're going to return low at the end. Almost. The 13th. Answer is 9. No 10. Ain't no 10, man. Why would I give it 10? Right, so either m, so have that many smaller than this, that many smaller than this, and eventually we'll have, shouldn't we find the smallest? Hold on, maybe we need to find, so 10 works, right? But what we need to find is the smallest such value, because there are gaps, right? There are gaps. If it's equal, I return immediately. So I need to push on the gap. So the first one, yeah, so it should be the first one. So this should be else. And else, that's going to be high is equal to mid. There we go. So because there are gaps, right? There are gaps. If and low is very aggressive. The low is because if count is this, we definitely have to plus equal to 1. Now the high will stay. High does not go. So it is possible, like in this 4x4 case, 9 and 10 both are ranked the same, right? So we first reach 10 because high goes down. We first reach 10, and that is not the answer. So we have to keep going, and then we go too small. Then we push. So it's the first one, first value that we hit. How do we make sure the first value we hit is actually correct? Why? Why the first value we hit is correct? For a smaller integer, yeah, that's true. times x, then it must be the smallest integer, which satisfies enough. If x is not in the table, then all the values in the table which are smaller than. If it's not in the table, then there definitely will be another one smaller than you that can also make it work. Nice. Yep. Wow. Binary search. The official solution. I got the idea that we need to count. I got the idea that we need to count the number of values, right? Of values smaller than a certain number. The count number of and use that count to determine if we hit k. However, the brilliant part of the solution is the counting and binary search for sure, but counting is the counting. Given any value, right, we can count the number of values on each row that is smaller than the given value by value divided by row number, right? Row index. Value divided by row index. Now this is the key insight. The rest is just So overall is log mn, and so m times log m times n. Oh man, binary search. I'm so bad at binary search. It's not the first time like fail at a binary search. Wait a second. All right. Wow, it's a tough one. It's a tough one. Very, very tough. But it's a good one. I'm gonna put this. Add to list. Yeah, we failed. So we add to nightmare. All right. That'll be it for today. Wow, tough one. I'll see you guys tomorrow. Adios.